Hello and welcome to lecture number 15 in the course Computer Graphics. As usual, we will start with a quick recap of the pipeline stages that we are currently discussing. So, as you may recollect, there are 5 stages in the graphics pipeline. First stage is object representation, second stage is modeling transformation, third stage is lighting or assigning color to the surface points. Fourth stage is viewing pipeline, which itself consists of 5 sub-stages, namely viewing transformation, clipping, hidden surface removal, projection transformation and window to viewport transformation. The fifth and final stage of the graphics pipeline is scan conversion. I would like to emphasize here again the fact that although in this lecture or in this course I will be following this sequence of stages, but in practice it is not necessary to follow this exact sequence. So, when a graphics package is implemented, you may find that some stages are coming after other stages, although in the sequence that I have discussed, they are actually before those other stages. Like hidden surface removal may come after scan conversion, although we are discussing it as before scan conversion. So, this sequence is not a strict requirement. The basic concepts are what matters the most. So far we have completed our discussion on the first 2 stages, namely object representation and geometric or modeling transformation. Currently we are discussing the third stage, that is lighting or assigning color to the surface points. In the lighting stage, we have introduced the basic issues that are addressed in this stage, and in the previous lecture we have gone through a simple lighting model. If you may recollect, in the simple lighting model we assumed that the color is essentially a composition of 3 constituent colors or the intensities: intensity due to ambient light, intensity due to diffuse reflection and intensity due to specular reflection. And we have learned models for each of these components and how to combine those models in the form of summation of these 3 individual components. Today we are going to discuss shading models, which is related to assigning colors to the surface points, but in a slightly different way. Now, as we have seen during the simple lighting model discussion, the model itself is computation intensive. So, the calculation of color at a surface point in a 3D scene involves lots of operations. As a result, generation of the image, which includes assigning colors to the image, is a complex and expensive in terms of computing resources. What are those resources? Processor, memory and so on. Also it takes time. So, both are important, resources and time. So, when we are talking of assigning colors or computing the colors, which is the job of the third stage, what we are referring to is essentially utilization of underlying computing resources. And in the lighting model we have seen that the utilization is likely to be very high because the computation involves lots of mathematical operations involving real numbers. Also, it is likely to take time. In practice, whenever we use some graphics applications, we may have noticed that the screen images change frequently. For example, if we are dealing with computer animation or computer games or any other interactive application, so screen content changes at a very fast rate. So, the requirement is that we should be able to generate newer and newer content and render it on the screen very quickly. But if we are getting bogged down with these lots of complex computations for assigning colors, or as we shall see in subsequent stages for doing other pipeline stages, pipeline operations, then that requirement may not be fulfilled. We will not be able to generate images quickly. So, that may result in visible flickers, distortions, which in turn may lead to irritation and annoyance to the user, and we certainly do not want such situation to occur. In order to avoid such situations, by reducing number of computations involved or the amount of computations involved in assigning colors to surface points, we make use of shading models. So, the idea of shading models is that we have lighting models, we can make use of it to find out or determine the color at a given point. However, if we do that for each and every point, then that is likely to be computation intensive and time consuming. To reduce computation, we use some tricks in the form of shading models. So, what we do with a shading model? First, we use the lighting model to find out or compute colors of only few of all the points that are there on the surface. Now, using those computed points, we perform interpolation, and through interpolation we assign color at other surface points, which are mapped to the screen pixels. So, here shading models are used when the surface points are already mapped to screen pixel. So, already rendering took place. Now, between lighting model and shading model, there are broadly two differences. We have already mentioned that lighting model is very expensive because it involves large number of operations, floating point operations. In contrast, shading models are interpolation based. That means we can come up with efficient incremental procedures to perform the computations rather than going for complex floating point operations, as we shall see in our subsequent discussions. The other major difference is lighting models are applied on the scene description, that means in 3D world coordinate system, whereas as we have just mentioned, typically shading models work at the pixel level after the scene is mapped to the screen or after the rendering is done, that is the fifth stage of the pipeline is performed. So, as I said at the beginning, it is not necessary that everything should work as per the sequence we have outlined. In practice, things work with a slightly modified sequence. What is important is to know about the basic concepts rather than sticking to the exact sequence of pipeline stages. So, that is the idea of shading model. and there are two major differences between lighting and shading models. Now, let us try to have a look and try to understand some shading models briefly. We will start with the simplest of the shading models, that is flat shading. So, it involves least amount of computation, and what it does. So, first in this flat shading model, what we do first is find out the color of any one point on a surface using lighting model. So, we apply the lighting model and compute the color of any one point, a single point on a surface, and then this color is assigned to all other surface points that are mapped to the screen pixels. So, suppose this is a surface and this is mapped. This is the pixel grid what I am drawing here. So, this, suppose consider this scan line here. So, the pixels that are part of the surface are these three. Now, what we do in this flat shading model is that we choose any arbitrary point, apply the lighting model and compute its color of that particular point in the 3D world coordinate system, because we require to compute the vectors also, and then we use that to assign colors to all other pixels that are part of the surface. So, suppose we have computed color at this point, say the color is C at this point, then we use this color to set color values of all other surface pixel points. For example, these three we set as C. Clearly, this is a very simple scheme and it is likely to lead to unrealistic images unless we choose the application scenario properly. So, we may say that flat shading works in certain situations, but not in general good to color any surface. So, in general we will not be able to use this particular shading technique because it may result in unrealistic images. So, when flat shading will be useful, there are few conditions. What are those conditions? Let us see. So, in order to make the particular shading method work, we have to assume three things. First, the surface should be polygonal. Second, all light sources should be sufficiently far from the surface, so that the shading effects, shades of different intensities or colors are not applicable. And third, viewing position is also sufficiently far from the surface. It may be obvious that if we are assuming that the light source is very far away and the viewer is also looking at the scene from a very far distance, then the minute differences between colors at neighboring regions may not be perceivable to the viewer, and accordingly whatever color we assign will look like uniform. So, in that case flat shading may work, and these three conditions restrict the use of flat shading algorithm. I repeat again, in order to make the flat shading work, there should be three conditions satisfied. First, the surface must be polygonal in nature, all light sources should be sufficiently far from the surface, and the viewing position should be sufficiently far from the surface. If these three conditions are not met, then the resulting colored surface may look unrealistic. To avoid the problems that are associated with flat shading, an improved shading model is there, that is called Gouraud shading. Let us try to understand Gouraud shading. It gives us more realistic coloring effect than flat shading, but at the same time it is having more computation. So, the improvement is at the expense of increased computation. What happens in this shading method? First, we determine the average unit normal vector at each vertex of a polygonal surface. We will soon see what we mean by average unit normal vector. Then, using that vector we compute color by applying a lighting model at each vertex of the surface. Then we linearly interpolate the vertex intensities over the projected area of the polygon. So, three stages are there or three steps are there. In the first step, we compute average unit normal vector. In the second step, we compute color at the vertex positions by considering the average unit normal vector, and in the third stage, we linearly interpolate the color that we have computed at the vertices of the surface to assign color to other pixels that are part of the surface. Now, let us try to understand these stages in details. So, in the first step, what we do? We compute average unit normal vector. It essentially implies that a vertex of a surface may be shared by more than one surfaces. For example, consider this vertex here. Now, this vertex is shared by all the four surfaces in this figure. So, in that case, when we are trying to compute color at this vertex, which surface normal I should use? So, there is a confusion. In order to avoid that, Gouraud shading tells us to compute average unit normal vector. This is essentially the average of the unit normals of the surfaces sharing the vertex. So, in this particular example, the vertex here is shared by four surfaces, each will have its own normal vector. Say for surface 1 it is n1, surface 2, surface 3 n3, surface 2 n2, surface 4 n4. We take the unit normal vectors, then compute average using this simple formula. So, this is a vector addition divided by scalar quantity, which is modulus of the 4 unit vectors. So, at that particular shared vertex, we use or we compute the average unit normal. Then, in the second step, with the average normal, we compute the color at this vertex using simple lighting model. So, if you may recollect from our discussion on simple lighting model, to compute color components for diffuse reflection and specular reflection, we had to use surface normals. So, instead of that regular surface normal, we use average surface normal to compute color, and this we do for all the vertices of the surface. So, take one surface at a time and compute colors for all vertices that define that particular surface. In the third step, which is the final step, we use these vertex colors to linearly interpolate colors of the pixels that are part of the projected surface. So, we are assuming here that the surface is already projected on screen through the final stage of rendering, and we already know the pixels that are part of the surface. Since we have computed the vertex colors in the first two stages, we use these colors to linearly interpolate and assign colors to other pixels that are part of the surface. Let us try to understand in terms of one example. So, in this figure, we have shown a projected surface defined by three vertices: vertex 1, vertex 3, vertex 2. So, if we apply Gouraud shading, after the second step, we have already computed the colors of these three vertices by using the simple lighting model as well as the average unit normal vector at these vertex locations. Now, we are interested to assign or find out the colors of the pixels that are part of the surface, but not vertices. For example, there are pixel 4, 5, 6, 7, these are all part of the surface, also 8 and many more. 4, 5, 6, 7 belong to the same scan line, 4 and 8 belong to two consecutive scan lines. So, what we do? We perform linear interpolation in terms of the colors that are already computed for the vertices. So, we take one scan line at a time. For example, we have taken the I plus 1th scan line. So, we compute the color at 4 and 7, which are two edge intersection points on the scan line. That means, they are the intersection points between the edges of the surface and the scan line, and we apply interpolation, where I1 and I2 denote the intensity or the color value that is already computed at vertex 1 and vertex 2. So, for I4 we require these two values, for I7 we require I3 and I2, where I3 is the vertex color at 3 here. And this y4, y2, these are all y coordinates of those pixels. So, we first compute colors for I4 and I7 on the same scan line, and then using I4 and I7 we compute I5, which is here, which is inside the projected surface on the same scan line. So, the interpolation is shown here. I5 is computed in terms of I4 and I7. Note that here we are using the x coordinates of the pixels. In order to compute I4 and I7, we used y coordinates, but in order to compute I5, we are using x coordinates of the corresponding pixels. That is about the same scan line. What happens when we want to compute color of subsequent scan lines? Say, in terms of previous colors, we want to compute color for 8th pixel, the 0.8. That is also possible actually the equations or the formula that are shown in the previous slide are not what is implemented in practice. There are more efficient implementation of Gouraud shading where we do not necessarily always compute the ratios and multiply it with the color values as we have seen in the previous slide. Instead, we perform interpolation with only addition. The multiplication and division are not required. However, for more details on this incremental approach of interpolation, you may refer to the reference material mentioned at the end of this lecture. We will quickly have a look at the corresponding algorithm. The incremental approach is encapsulated here, these two lines. As you can see, color can be found out by simply considering the color already computed plus some edge constants which are predetermined. Similarly, in this stage also, in this stage we can use simple addition to compute color, where the addition is between previously computed color and some constant which is already pre-computed as shown in this line 2. For more explanation on this algorithm, you may refer to the material that will be mentioned at the end. The basic idea is that this linear interpolation can be computed using simply addition rather than multiplication and division that are required if we are trying to do it in a classical way. So, this is more efficient implementation of the stage 3 of Gouraud shading. And one more thing we should note here is that this particular shading technique, Gouraud shading, is implemented along with a later stage of the pipeline which is part of the fourth stage. It is called hidden surface removal. So, we will discuss about it later. So, Gouraud shading assigns colors, but it is typically implemented along with a later stage of the pipeline, that is a sub stage of the fourth stage, hidden surface removal. There are problems with Gouraud shading as well, although it generates more realistic images compared to flat shading, but there are two major problems. One is it is still not good to generate specular effect, that is that shiny surface or the bright spots that we get to see on a surface. This is primarily because this linear interpolation results in smooth change of color between neighboring pixels, which is not what happens in specular reflection, where there is a sudden change between neighboring pixels. Secondly, Gouraud shading suffers from this problem of occurrence of Mach bands. This is kind of psychological phenomena in which we see bright bands when two blocks of solid colors meet. So, if two consecutive surfaces are assigned different colors, then at their joining point we may get to see some band like things, which is a psychological phenomenon known as Mach banding effect, and this results if we apply, this may result if we apply Gouraud shading. There is a third shading method which is quite advanced and it eliminates all problems that we have discussed so far with flat shading and Gouraud shading, but it is heavily computation intensive and requires huge resources as well as time. We will just learn the basic idea and we will not go into the details. So, this Phong shading is also known as normal vector interpolation rendering. Now, in this we actually compute color at each point where we find out the normal vectors in a different way. So, there is actually no interpolation involved, interpolation only in terms of finding out vectors, but not computing colors. It takes much more time as expected, and it does not have the advantage of other shading models in terms of reduction in computations. So, it gives us very realistic image because the coloring effect is closer to reality due to the very sophisticated approach, but for the same reason it cannot compute colors with reduced computations, which is the advantages of shading model. So, it is not having the main advantage, but it gives us more realistic images. We will not go into the details of it, it is quite complex, and if you are interested you may refer to the reference material that will be mentioned at the end of this lecture. I will just mention the 3 steps. In the first stage, we compute the average unit normal vector like in Gouraud shading. Stage 2, we apply the lighting model at each vertex to compute color, and in stage 3, we apply interpolation, but in a different way. What is the difference? Instead of interpolating colors, we now interpolate to determine normal vectors at each projected pixel position. Remember that normal vectors assumes that we are in 3D world coordinate system, whereas projected pixel position assumes that we are already in device coordinate system, which is 2D. So, we need to calculate normal vectors to actually apply the lighting model, which involves use of normal vectors. We do that here in Phong shading. So, the interpolation is not used to compute intensity, instead it is used to determine normal vectors. Once that is done, at each projected pixel we know the normal vectors through interpolation. We compute color using the lighting model. So, here we are computing color using lighting model, but not through interpolation. Only difference is that in order to compute color with the lighting model, we need normal vector, which we are finding out through interpolation. So, essentially in this case, if we summarize, the surface is projected, we identified set of pixels that constitute the surface. At each pixel location we are applying the lighting model. Before that we are using interpolation to find out the normal vector at that pixel location, and then we are using the lighting model. So, we are using lighting model repeatedly, which increases the computation and time. For more details, you may refer to the material that will be mentioned at the end. We will just outline and we will stop here on the discussion on Phong shading. Now, let us try to understand the idea of shading in terms of one illustrative example. Let us consider a cubical object with the vertices given A, B, C, D, E, F, G and H. Now, with this object we want to create scene of a room in which the object is treated as a self attached to a wall, keeping the relative positions of the corresponding vertices same. So, the relative position will be same, and there is some specification about the wall also. It is parallel to the xz plane, cutting the positive y axis at a distance of 1 unit, and the length is reduced by half, and we also mentioned the corresponding vertices in the self with respect to the original vertices. So, after the specified transformation, this is a 3D, this figure shows the 3D scene with the self attached to the wall as specified in the problem. We also have to know its projection in order to be able to apply shading. Now, that is mentioned here. The self looks something like this as shown here, with the vertices specified, which each of which correspond to the corresponding vertex in the original scene. So, f dash dash belongs to f dash, e double dash belong to e dash, and so on. And in the projected scene, we have mentioned one vertex coordinate, so that other coordinates can be derived. For example, here we have mentioned the vertex coordinate of 4 7, then we can derive E to be x will remain same, y will be reduced by 1 2 3 4 5. So, y will be 2, and so on for other vertices. In that way we can derive the locations. Now, assume that the room has a monochromatic point light source at a given location with intensity 2 units, and also assume there is an ambient light with intensity of 1 unit, and the reflective coefficients or reflectivities for the 3 components Ka for ambient light, Kd for diffuse reflection due to direct light, and Ks for specular reflection due to direct light are specified, and specular exponent is also specified as 10, and the viewer is located at this position. Assuming this setting, let us try to compute the colors at the pixels P1, P2 and P3, assuming the simplest of the all flat shading. So, this is P1, this is P2 and this is P3. How we can do that? So, we first determine the coordinates of the projected vertices, which should be easy. Then we have to compute the color at any given point on the surface. Note that as per the problem description, light source is above the surface A dash, B dash, C dash, D dash, and on the left side of the plane which contains the surface B dash, F dash, G dash, C dash. Thus, it will illuminate this surface, but will not contribute anything towards the illumination of the other surface. So, this is first observation from the problem description. Now, in order to compute color, we can calculate color at any point and then use the same value throughout the surface in flat shading. So, let us calculate color at this vertex B dash. If we see the scene and the object description in the scene, then we know that surface normal at B dash and the unit surface normal will be this. Now, we know the light source. So, the unit vector towards the light source can be computed in this way and unit vector towards the viewer, because we know the viewer location, can be computed in this way. Then with these values we can get the dot product as something like this, and also this second dot product for the specular component as something like this, and with these values and using the reflectivity coefficients we can get the three components added up to get the overall color value to be 0.79 unit at B dash. Now, we know that P1 and P2 both are part of the same surface containing B dash. P1 is part of B dash and P2 is part of the surface containing B dash. Now, if we are using flat shading, so we have already computed the color at B dash. So, we will simply assign these colors to all the surface points, that means to P1 and P2. So, the values, color values of P1 and P2 will be 0.79 unit. And we have also noted that the light source do not contribute to the illumination of this other surface B dash, F dash, G dash, C dash. So, in that case there will be no contribution due to direct light source. So, those two components due to diffuse reflection and specular reflection due to direct light source will be 0, and it will be illuminated only by the ambient light, which is computed using this expression K into IA, where K is the coefficient value and IA is the intensity, and we get this value. So, these are the values that we have computed using flat shading P1, P2 and P3. Note here that we did not use color model or the lighting model to compute values at P1 and P2. Instead, we computed the value only at B dash and use that to assign color to P1 and P2, and similarly we have done for P3. So, here we have reduced the usage of simple lighting model, and by that we have reduced the amount of computations required. However, as I said before, since we are using flat shading, the colors that are computed may not look realistic when they are rendered on screen if the distances of the source as well as the viewer from the surface is not sufficiently large. Now, here also it may be noted that we have done some informal reasoning to come to the conclusion of the color values, but if we simply apply the algorithms, then also we will get the same result. We do not need to actually do any informal reasoning, but that you can try on your own. We will not work that out here. And also I would like to request you to use Gouraud shading algorithm to perform the same computations for the 3 points. I leave it as an exercise for all of you to do. and then you can compare the amount of computation as well as the kind of values that you are getting, and from there you can get some informal idea of the effect that results in the application of these different shading models. So, we have come to the end of our lecture today. To quickly recap, we learned about the idea of shading and its difference with the lighting model. Then we discussed in details flat shading model and Gouraud shading models, and just outlined the idea of Phong shading models. With the illustrative example, I hope you could get some idea of the application of the shading models and its advantages over application of only lighting model to compute colors. With that, I would like to end today's lecture. For more details, including the ones that are mentioned at different points of the lecture, you may like to refer to this book. Please have a look at chapter 4, section 4.3 for the details on all the topics that I have covered today. Thank you and goodbye.